And this will be the final workshop in the series Quantum Chemistry with Python. And I'm the creator of this workshop. My name is Vinayak. I'm a graduate student in University of Kentucky, and my research is in computational chemistry. That's where all these workshops that I've been conducting are concentrated on computational chemistry. All the things that I discuss come from my research experience in doing these things. So this will be the final workshop in the 3-session series. So in the first session, we discussed about input structure generations, how we could generate a single molecule or combination of molecules using RDKit. And then we moved into running some DFT calculations and understanding what basis sets are and what a DFT functional is. And then we optimized the geometries and did some frequency calculations. And in this final session of ours, we'll look into how to use those understandings and the expertise or skills that we gained in running DFT calculations to actually apply them to real world problems, and how it's applied to get molecular properties and get absorb maybe run a time dependent DFT calculation to get the absorption spectra. And we'll also look into some corrections, like how we are going to correct for solvents. And all the things that we are discussing over here will be using PySCF for doing the DFT calculations, but the things we are discussing here, the concepts are applicable to other quantum chemistry softwares too. And there'll be some changes here and there, but the basics still remain the same. And this workshop is recorded, and all the videos will be on the YouTube channel of Chemistry with Code. And make sure I'll appreciate if you'd like and subscribe it so that you are notified about the videos and the events that will be happening. So do you have any questions so far about the workshop or anything? Yeah. So we'll move quickly into the final session of ours, and let me just share the link of the GitHub page that we are going to use. And you might have received this in your emails that are sent by the event management stuff. So this is the link, and once you click onto this link, you'll be directed to this GitHub repository of mine, which is Quantum Chemistry Introduction. And today we are going to use the DFT for computing molecular properties, that notebook that you see. So you can click on it, and once you click on it, it will open a different page, and here you see this button which is open in Colab. Once you click on that, you'll be taken to a Colab notebook. So if you are at this point, do give me a thumbs up or let me know you are here so that we can proceed. Or if you have any questions, if you have trouble getting here, do let me know. Oops. My bad, I didn't share the screen. Okay. So this is the page you'll be taken to if you use that link. This is the GitHub page, and then click on DFT for computing molecular properties, and then open Colab. Okay. This should take you to the thing that we are going to work with. So can everyone see the screen that I'm sharing? Can you see my web browser? Yes, cool. So yeah, so if you're at this point, let's get started. So if you are not used Google Colab before, This is a Jupyter notebook kind of environment, and this will help you run calculations without installing any softwares on your local machine. So to run something, this is a cell, and if you want to run, you can press the play button, and it's going to run whatever code you put in the cell. So let's start first by installing some of the packages that we need, RDKit and PySCF. So just click on this play button, and it'll give you some notice, and then say run anyway. It should start running. So
Hi, Vinayak.
yeah.
I'm sorry I interrupted you. So I did not follow the previous session. So you had probably told us to install Avogadro or something of that sort, right? I did not install any of those things on my local machine. So is it fine if I go along with the collab?
Yeah, so collab, we are going to run all the calculations in this collaboratory, and just Avogadro is just for visualization. So you can follow along as I show some things in Avogadro, but we are not going to do a lot of calculation. We are not going to use Avogadro for any calculations. All the calculations are done in this collab. So you'll be fine if you don't have Avogadro. In that part where I use Avogadro to show something, you can just follow along.
Okay, cool. Thanks.
So yeah, so just click on this play button and let me know if you have installed so that we can proceed to the next step. Give me a thumbs up or something. Okay, so there's one. Okay. Cool. So let's now move on to what we are going to do in this session. So in the last two sessions, the link of the recordings over here for first and second session, we looked at running DFT calculation. That is basically what we started to do. And we learned, we looked at how to generate structure and run DFT calculations, but we did not see how we can actually apply those calculations to get molecular properties or the way it's used in research today, where we use all of these techniques for comparing experiments. So that's what we are going to do today. And we'll see how to obtain molecular properties and compare them with experiments. It's okay if you have not attended the previous sessions. All the things that are needed for this sessions are contained within this session. So you can just follow along. And if you have any questions, you can ask me. Yeah. So first thing that we're going to do is once we run a DFT calculation, a single point energy or self-consistent field calculation, we get some energy, and I'll show you that over here. So once we solve the ConChem equation, that's what we are solving, we get energies. And what people are really interested in sometimes is for finding the HOMO or LUMO of the molecule. And HOMO is the highest occupied molecular orbital, and LUMO is the lowest unoccupied molecular orbital. So the gap between the HOMO and LUMO is sometimes what people look at because of transitions that are happening. We'll delve into that later as we follow along this session. And it's also how much of energy you would need to remove an electron from HOMO that's more into ionizing the molecule or reducing the molecule. So getting a sense of what the energies are for HOMO and LUMO is critical for comparing them with experiments. So we'll first start with that, okay? So we'll import all these definitions. So we have installed RDKit, and these are some of the definitions that we are going to use. And if you want to see how we generate a molecule, you can go back to the first session. But in brief, it's like you give it a SMILES representation, you generate a 2D structure, then add some hydrogens because we are missing hydrogens, and then generate a 3D structure. And this is where we are generating it. We save it as an XYZ file to use it for DFT calculation. And this part of it is the DFT calculation. Sorry. So we use the geometry that we created. We use the basis set 631G. You can use any other basis set you like. functional, we are using B3lib over here. Again, you can use any other functional that you're interested in, and then run the calculations. So this is what we had done in the first two sessions almost. And you get the energy of the molecule. So this is the energy of ethene. Ethene is 2 carbons with a double bond in between. And this is the energy right now. So if you want to look at HOMO of a molecule, some packages directly give you the values of it. So if you look at Gaussian Psi4 or something like that, which run electronic structure calculations, they'll give you HOMO and LUMO. But if you want, you can get it even manually. And over here, we'll see how we can get the HOMO and LUMO just by some math or some simple arithmetic. Okay. So if the first step is in getting the HOMO is to get the total number of electrons in the system. So once we get the number of electrons, we know that electrons will be paired together. So there'll be 2 electrons in one orbital. So that means that the HOMO will be the n/2 orbital. Okay, because 2 electrons are pairing, so only half of the orbitals will be filled. So n/2 is what you'll be looking at. So if you want to do this in PyCF, you can do it in any software that you want. Just look at the total number of electrons. So the total number of electrons in our system is 16. And once you run a DFT calculation or any electronic structure calculation, you'll get orbitals. And the MO energies or orbital energies are referred to those energies of the orbital. So here we have some orbitals, like 14 orbitals, and only some of them are filled because we have only 16 electrons to be filled in these orbitals. So it starts pairing electrons from here. So 2 electrons in this, 2 electrons in this, 2 electrons in these, and so on. So now if you want to find the HOMO, it should be the 8th orbital from the lowest number, right? So this is the most stable orbital, and then you start filling up. So the 8th orbital is what we want. And if we do it n/2, will give us the 8th orbital of this. This is a list. This is like a list. So we can subscript it and get the n/2 orbital. But the thing is, Python index starts from 0. So we just subtract 1. So this will should give us the 8th orbital, which is 1, 2, 3, 4, 5, 6, 7, 8. So this is what we need, because the HOMO is the n/2 orbital. So we see that we get the HOMO value. And then the LUMO is the next one. So you can just change the indices here and then look at the LUMO, LUMO +1, LUMO +2, and so on. Okay. And all these energies that you see in most of the electronic structure program are in Hartrees. And Hartree is a unit of atomic energy. So to convert into electron volts, you can just multiply it by this constant, and this is the value in electron volts. So the HOMO of our molecule is at this electron volt. Okay. So you can get LUMO and all those energies, but if you look at some of the research papers that are published, they show the HOMO and LUMO. They visualize it. And if you want to visualize it, we can use this code that we have here in this cell. And once you run it, it'll generate the orbitals in this Molden file. And depending on what computational software you're using, sometimes it may be called cube file if you're using Gaussian, maybe even Psi4, any of those softwares. But essentially, you will be generating some volume or electron density maps, and you can visualize them. That's what people represent those molecules, the orbitals into. So if you run this code and click on these files over here, you will see that we have the XYZ that we generated initially. The Molden file is the one with molecular orbitals. So you can download this file. And if you have Avogadro installed, you can open this in Avogadro, or you can just look at what I'm doing, but there's nothing, no calculation being run. All you need to do is visualization. So you'll see a molecule, and over here you see the orbitals. So the energy is not shown because the format is not correct for energies. We don't have energies into it, but we can visualize the orbitals that we want. So if you want to look at HOMO, just click on HOMO. We see that this is the HOMO orbital. Just to make sure, can you see the Avogadro with molecule in it? Just to make sure I'm sharing the right screen. Yes, okay. So yeah, so this is ethene, and if you remember, if you have taken any physical chemistry course or organic chemistry course or something like that, you might have seen that we have two p orbitals, and those two p orbitals combine to give us this HOMO of ethene, and they are combining in symmetric way. So you would see the positive lobe on top or negative lobe at the bottom, and this is the HOMO of ethene. And you can even look at LUMO. You can just click on that. You'll see that we have a symmetric combination of those p orbitals, and then we have the anti-bonding orbital, and this is what it should look like. Okay. So this is just the visualization part, and if you don't have a Avogadro, it's okay. If you have Avogadro, you can visualize all the LUMO +1, all those orbitals into this. So going back to this, so what we are going to do now is a little bit of exercise where your task is to get the HOMO-LUMO gap for benzene. So you're going to run the calculation that we did above, just a SCF calculation, but you are going to do it for benzene, and use this level of theory to run it. And if you want to, I should have mentioned it, how to get smiles for benzene, but you can use pub structure to smiles. I should have given this thing, but it's okay. Oops. So this is what I recommend to use, smiles to structure for PubChem, and you can draw a benzene ring here and then copy these things on top for the smiles. I can put this in the chat. So those are the smiles that you need. So we'll spend a couple minutes here, and if you have any questions, you can ask me. And if you have any trouble getting the HOMO-LUMOs, to let me know. So there's one question, which is how to open orbitals in Avogadro. So to open orbitals, first you need to generate them, and you need to run a calculation, SCF calculation. That's what we did above. And if you run this code over here, it'll generate Molden file, which has the information about the orbital. And to look at the Molden file that is generated, click on this files button over here, and then you will see the Molden file that is generated. So click on those three little dots that you see, and then download the file. So this should have information about, let me just clear this stuff. Let me just close it down. So then, oops, avoid using. I'll use Avogadro, open Avogadro, and just open the file that you have in Avogadro. And I just push it into Avogadro. And you should see something like this, which are called orbitals here. And these are the ones that you would look at. It should open this panel for you. And to visualize it, you just need to click on which orbital you want to visualize it. So if I want to visualize LUMO, I just click on LUMO and it will show me the LUMO. I hope this works. So we'll just open the Molden file in Avogadro. It should open. So was anyone able to get the homo-LUMO gap for benzene? So you'll do the thing that we did above. This is for the HOMO, but just change it to benzene and then you won't get the LUMO. Okay. So question about not getting the panel. So once you open, the panel usually is hidden up somewhere, but if you load, yeah, it's not this far. But download and then Molden, open Molden. So you can just go to settings and look at toolbars and make sure your orbitals toolbar is over there. And if you don't have that toolbar, it won't show up. But if you go to settings, toolbars, and then orbitals, it should show up. Okay. Let me know if this works for you. And then you can click on those orbitals. It should show. Okay, so we just have some more things to go over. So we'll quickly go over that and make sure that we complete the things that we intended to do in this session. And we'll have some more time for further discussion at the end. Okay. So what we did earlier was for neutral systems. Now we can look at charged systems. So +1, +2, +3 states, or if you want to remove electrons from the system, add electrons into the system, we can even run those calculations. So to do those, it's same as the earlier things that we did for neutral molecule, but the things that we need to change are the charge of it and the spin of the molecule. And it's standard for any electronic structure program that you're going to use. You can't usually set where you want to put that charge in, but it just says that you remove an electron or add an electron from it and then do the calculation. Okay. So in this case, we'll look at +1 charge. So we are removing electron from ethene molecule. So we'll say charge is 1. And if you want to put a negative charge, it'll be charge of -1. So, and charge of -1 represents you adding an electron to the system. So we have charge of 1. And this is also, once you put the charge as 1, you also need to tell the program as to what the spin is of the system. By default, the spin is set to 0 in most cases, and the spin represents how many unpaired electrons you have. And S is the number of unpaired electrons. So because in this system we are removing an electron, we have 1 unpaired electron, and the spin of that should be half, because all the other ones are paired. And so 1 electron spin half, so it will be 2 times S. So 2 times half is 1. So we set mole.spin equal to 1. In some of the codes, instead of 2S, there's need of this formula, which is 2S plus 1. So if you're using Gaussian to run calculations, you will use 2S plus 1 to do it. And in that case, the spin would be 2. So it is very dependent on what type of code you are using, but you need to set both of them, charge and spin, for running calculations for non-neutral species. And for neutral species, the charge would be 0. and yeah, charge would be 0 and spin would be a singlet. Okay, or in this case, spin would be 0. It depends on how you set this. So it'll be spin equal to 0 if they're all paired. If you're using some other code, the spin equal to 1. But make sure to look at the documentation of how it's done in that particular code. But you need to set both those parameters. And once you run it, it does the same thing, but now with different number of electrons. So you get different values for SCF energy. So what we can do now is to compute the ionization energy of the molecule that we have. And that is basically the difference between the neutral energy and the cation energy that we just calculated. And over here, I just multiplied by the scaling factor to convert it into Hartrees. And this is the ionization energy for ethene that we have. And you can do it, you can compare this with value with what people have reported, but just keep in mind the value that we get here is in gas phase. So we don't have any solvent around it. So this value is in gas phase, and the temperature at which these things are done is at 0 Kelvin. So there may be some discrepancy with experiments that are done because they are at different temperature. We don't consider any other entropy or entropy contributions to this. So there are ways in which you can do it, but that may be a topic for some other day to discuss. So this is the enthalpy that you are getting from, if you look at Gibbs free energy, this is the enthalpic part. We still need to consider the entropic part to do stuff, but this should be a good enough approximation to ionization energies. So if you have any questions, do let me know, or just try out this exercise, which is calculating electron affinity for benzene. And it's instead of removing an electron and setting charge to +1, you'll be doing it for -1 in benzene. So we'll spend a couple minutes. You can just copy paste the above code that you have written if you have done it for if you have generated orbitals, the HOMO-LUMO gap for benzene. You can just copy paste the code, make a little change, and then get this thing. We'll wait for a minute, and if you have any questions, do let me know. And if you already got the electron affinity for benzene, also you can put it in the chat and say, oh, this is the value that I got. Oh, you got the value. You can just even give a thumbs up or something. So there's a question which is, so there's a question which is, for executing many optimizations, we need use for with Python or PySCF1 method. Okay, so I think the question is, if you want to optimize a molecule, do we need to use a for loop, or do we just use the PySCF optimization? So the answer is, whenever you use optimization in any electronic structure code, you're just going to use one optimization. It'll just be one calculation that you're going to run, and there's the for loop within that code that is running. So you need not put another for loop to loop it over again. So there's just one calculation that needs to be done. But right now you can just not do optimization and just do single the SCF calculations to get the energies that we need. I hope that answers your question. Okay, so let's move on. And the next one is about solvents. So as I told you earlier, we have gas phase calculations at 0 Kelvin, but we can make some adjustments to it to include solvent. One way to include solvents is to add the molecules explicitly. So if we have benzene and if you want to add water, you can add water molecules into the file and say, okay, this is the geometry that I'm going to use. But it takes more time to do those calculations because we are increasing the number of atoms in the system. So what we could do is, instead of saying, okay, these are the solvent molecules that we want to simulate the effects of, you can say, okay, consider this to be a dielectric medium. So we only consider the dielectric constant for the solvent that we are going to use, and say that while doing calculations, you move the charges around based on this dielectric constant. So because we have a dielectric constant acting, the molecule may be polarized to move the charges according to the effects that it sees on this surface because of the dielectric constant we put in. And this is called implicit solvent. So where we did not put in molecules into it, but we just put in a dielectric constant and model the effects based on that. And to do that, there's a minor tweak that we need to do to the earlier code that we ran SCF for. So it'll be using DDSOs, and this is one of the solvent models that we have. PCM is another one which people use, but in PySCF, the Cosmo model is the one that is implemented. So we are going to use that. So we are going to set this thing with solvent.eps is this value, and this is for acetonitrile, and this is all we need to do. And if you want to put it water, you just change this value and run it. We're not putting any actual molecules in it, but we are simulating the effect with dielectric constant. And if you run it, it should give you some energy of solvent energy that we get. So again, single point energy calculation, and then can look at solvation. It's a solvation enthalpy that you have when you put water, acetonitrile and ethene. And if you want to look for what values that you need for different solvents, you can just click on this link and it should take you to the solvent models. And we are using this model, the Cosmo model, and the values that we need are over here. So I used acetonitrile, you can use water, methanol, and all of these. So you would need to just replace the values that you have here. The same goes in any other electronics calculation software. You can just specify the dielectric constant. It will run the calculations with those polarizations that are needed. There are a bunch of molecules that you can see. Okay. Any questions so far? So there's a question which says, have PySCF the SMD model? So SMD is another solvation model, and I don't think they have solvation model. This is the only solvation model that we can see here, but then you can do some embedding into it and then mess around. But you can look into the documentation and see whether they have something, but I couldn't find one. And the intent of this workshop is just to show you how it's done, and different methods will use different solvents. So different electronic structure codes will use different solvent models, and but the basic concept still remains the same. that you're going to put dielectric constant and then try to simulate it. So there's another question, which is it possible to do geometry optimization with solvent effects? Yes, you can do geometry optimization with solvent effects, and the thing will be similar to this. So all you would need to do is add these things into it. I think there was one which showed, did it show you? No, it did not show how it's done, but you can still use the same thing, which is with solvent. There'll be some tweaking here and there, but it should still be this thing. And if time permits, I can show you how it's done at the end of this workshop, but you can still do optimization with solvent effects. Again, the enthalpy, this is the enthalpic part, as I said, but if you want to calculate entropy, we need to put into some, we need to add some entropy and then get the free energy for solvation. So there's another question, is it possible to use mix of solvents? I haven't seen a mixture of solvents anywhere, but what I would possibly think of doing is, if it's a mixture of solvent, try to get the dielectric constant of the mixture, find the dielectric constant of the mixture and put that value into this, and then it's going to simulate it. Because it's the dielectric constant that matters and not the actual molecules that you put in there. So I hope that answers your question. Okay, so we'll move on to the final final topic that we are going to discuss, and after that there'll be some exercise which you can work on, and I'll be hanging around so that if you have any questions, you can ask me, or we can look into some other things. So this is the time-dependent density functional theory, and the things over here what we are going to do are very similar to DFT. So I won't go into the details of solving this Schrodinger equation and how it's done in how it's done for TDT DFT, but the things are very similar to the previous video that we discussed, that we are going to solve these equations, and we are going to use ConChem formalization to solve these equations and get the time dependent insights. So the reason we use time dependent is because we are going to look at excitation. So if you excite something and we need to see how it evolves in time, right? So it's not a static thing that we're going to do. So that's where we need time dependent calculations. And these are usually for getting optical excited states. So you can get your singlets, triplets, and all of those that you need for time dependent calculations. So it looks very much similar to the DFT calculations that we have done. We still use a basis set. We still use a functional. If you want solvent, we can add solvent again. If you don't want solvent, you can just run with this code. And in this case, I'm adding solvent. So we're adding solvent. So add solvent, similar to SCF calculations that we have run. It solves something very similar equations, but in this case, it's the time-dependent Schrodinger equation instead of just the time-independent Schrodinger equation. And those are ConChem formalizations of that we are solving. So this is how we would set it up. And in different softwares, you're going to set it up differently. But what matters is these two things that you set up. So TD singlets is equal to 2. So you can calculate, you can look at singlets or triplets. So singlet are states where you have spins combined like this, and when it excites, it still remains in that orientation. So the total spin is still 0. And triplets are when you excite something and it changes the spin. So then it becomes half and half spin, and that becomes 1. And if you use 2s plus 1, that gives you 3. So that's the reason we get triplets, because you have 2 spins, half and half, combined together, it's 1. So 2s plus 1. So S is equal to 1, so 2S plus 1 is 3, so it becomes a triplet. If they are paired like this, S is 0, so 2 times 0 plus 1 is 1, so they are called singlet. So you can get different states, and that's what you're going to set in any computational program that you're going to use. And then the number of states that you need. So if you need S1, S2, S3, the singlet 1, singlet 2, singlet 3, or triplet 1, triplet 2, triplet 3. So a rule of thumb is just to add like 10 more states to what you actually need, because it's trying to do some sort of fitting at the back of the scene and behind the scene. And the more states you request for, it tries to fit it more accurately into those states. So just give a larger number in you, and not too large, because if you are given a too large number, it'll take a lot of time for you to calculate if you calculate the excited states. So, and then we are going to run it with td.kernel, and this is a method that gives you a nice table at the end of excitations. So once you run it, it'll take a while. This is a small molecule, so it should run quickly. But if you're running it for something else, it may take a while to run. So as we see over here, we get singlet excitations because we request that singlet equals to true, and if singlet is equal to false, we'll get the triplet states. So we get singlet excitations, and the first excitation where energy is this, in nanometers is that, and the way we analyze it is using the F values that I knew. So the F values are indicator of kind of intensity of the oscillation, intensity of the excitation. So we see using this level of theory that we are using, the B3lib61G, and we find that this is not the prominent excitation. The intensity of this will be 0. And then we have this one, which is more dominant. So oscillator strength is 0.4 for this. So this will be the dominant excitation that we would see. So this is how we analyze it. And if you want to convert it into a nice data frame kind of thing, there was a question, can we put these values in a data frame? I think there should be ways of doing it, but you can just get inside all these excitations and put them into something. And that's what we're going to do in here. We're going to plot, instead of putting it into a data frame, we are going to plot it and see what the absorption spectrum looks like. So if you get TD object, so TD is this TD that you see over here, TD object dot E will give you all the excitations, and I just convert them into electron volts in here. And TD or oscillator strength gives you oscillator strengths, and then you can put all of these into a data frame if you want. But what we are doing right now is, given this oscillator strength and the excitations, we are going to put in Gaussians around the excitations so that we get the absorption spectra. And that is what the rest of the code over here does, just add some Gaussian functions. And the intensities are given by the oscillator strength. And this is a function that we are going to just run so that it's ready. And if you want to look at the absorption spectra, we just pass in the TD object that we created here, this TD object, and we just pass it into this absorption code, and then it should give you the absorption spectrum. And all we did was add some Gaussians onto those excitations that we saw. Oops. And this is what it should be like. Do you have any questions so far? And you can even do optimizations and all of those stuff, but that's I would suggest to look into the manual and see how it's done. You can add solvents. We did add solvents in this, but yeah. So any questions? So if not, we still have like 10 minutes, and that's good. So if not, we have reached the end of this sessions, the 3 sessions that we had, and this should give you some basic idea as to how you can run DFT calculations and compare the at least get the molecular properties and understand some things like what is the basis set, what functionals do we need to use, and what are those functionals, what's going on behind the scene. I hope those things were at least conveyed to you in this series of 3 workshops. And if you have any comments or suggestions, you can take the survey and let me know what your thoughts are. And yeah, so that's all about this part of stuff. And if you want to get a LinkedIn shareable certificate for this, what you would need to do is complete the task below, and we'll go through the task and I'll tell you what we are going to do in that. So once you complete the task, you're going to print this page, print this file as notebook. So if you go to file and print it, it should print, and then you're going to save it as a PDF file. Don't change the name of this, so it should be saved something similar to this. And you can then go to this page, click on this, it'll take you to a page where you need to upload the file, put in your name and email and all of that stuff, and it'll give you the certificate for this course. And if you have any questions, you can just ask me on Facebook or something that you are not able to get it. I'll make sure that you get the certificate from it. So this is more like a hands-on experience for you to actually use the things that we talked about and see how they are applied in research in chemistry. And what we are going to do is reproduce some of the results that are in this article, which was published in 2016, and it's a small molecule, which is amino bipyridine, and this is the molecule here in the graphical abstract of it. So what was observed in this was, if you synthesize this molecule and crystallize it, if you can go crystals out of it, there are 3 distinct crystals that you can go, and all of them show different colors. And the reason for that is because it's stuck at different orientations, the dihedral orientations. So what we're going to do is explore these orientations and see whether we can reproduce some of the computational stuff that was done in here. And do use B3LIP and 631G, and I think all the calculations were done at this level in this work, so you can just use that to see how it compares. So at first you would generate a 3D structure for this molecule, use the smiles and all of that, look into session 1, how it was done, optimize the structure in gas phase, and frequency calculations. This will be all of session 2 that we look that has all of this, and then generate the MOs for this and compare. So if you click on the SI, figure S10, I think so. Let's keep scrolling, yeah. So you see figure S10 that has these MOs, and you can generate your own MOs and see whether they look similar to this that was generated. And this is the same level of theory that we're using. But there's a polarization part, but you can just ignore it. Right now, we are just using star. Okay. You can compare these. The next task would be to see whether this is the experimental absorption spectra, the dash one in CSCl3 chloroform. So you are going to do it for the molecule with PySCF. We looked at how to add solvents, and you are going to try to do it and see whether the energies match with what you see in this calculation that you perform. And finally, you're going to perform the dihedral scan, and we are going to change the angle. There should be one over here somewhere. Let's see. There we go. So we are going to change the angle between those 2 phenyl rings, and we have discussed how to set or constrain stuff. in session 1. So you're going to try and do it for different angles, and maybe you can just calculate single point energies, just turn it, calculate energy, turn it, calculate energy. There's no need of optimization, and see whether you can get a similar curve for the energy. And this will give you some sort of barrier from moving from one structure to the other structure, and also give you what the global minima looks like. And once you do this, there are instructions on how to get the certificate, and you can get that. And if you want to participate in more of the workshops, do follow us on Facebook or YouTube, and you can have comments in YouTube. I'll try to respond if something is not working for you in that. Yeah. And the rest of the time, we have like 5 more minutes, so you can keep working on this right now. And if you have any questions, you can ask me. I'll try to assist you in the task that we have over here. Okay. So there's one question, which is it possible to see the transition orbitals? Yes, it's possible to see transition orbitals using any DFT code. In this particular instance, there are ways of doing it, and that's called, usually it's natural transition orbitals that people look into. Let's see. Quick start, NTO analysis. So NTO is what people usually look at. NTO. So this is NTO analysis. So this may help you to see what those orbitals are. And what NTO analysis does, it gets the orbitals that you can see, like HOMO-LUMO transition. Instead of HOMO-LUMO, you can see actual transitions as to what's happening. So you can do that in this, and I would say just look at the documentation, and that may help you develop the things that you need for getting the transition orbitals. But it should be in here. You can see some of that. So there's another question, PySCF for R language. It's a Python SCF. So I don't know whether they have a R language SCF. Yeah, you can see whether they have something like that, but maybe people have developed DFT codes in R, but I'm not sure. Any other questions? Can we calculate the local reactivity descriptors? So local reactivity descriptors, people, I think there was one question about something. Yeah. So reactivity descriptors, I think it should be something that PySCF can handle. You can look at things. I don't think it is there. Did I spell it right? Yeah. So it depends on the code that you're using, but I don't think it's in PySCF. It's done, but maybe other codes will help you. Like I know it's in Gaussian. You can look at Gaussian and then run that stuff. But PySCF is still under development. That's what they are developing every time, and then you may see hopefully some development. So
develop programs accessibility. It's learn from information.
I could, if there was a question, I didn't hear it. If someone unmuted themselves, you can repeat it, and if it was unintentional, it's okay. So yeah. So okay. So if you have any questions, I'll stick around for a couple of minutes, and you can try working through this task that you have and trying to upload it. It'll take a while, I know, but if you have any questions and as to how to proceed with the task, do let me know. And some of the next workshops. So this series was on how to run DFT calculations. The next one will be on machine learning and how to get started with machine learning from scratch, and do some of the things that we did in DFT. We'll be doing it in machine learning, but those workshops will be somewhere in November, not so soon. And before we conclude this workshop, there are pre-workshop surveys, and there were some questions asked in the pre-workshop surveys. So let me see whether I can. So some of the things were like, can you direct us to some free resources for all of this? You can just look at the documentation of PySCF and see how it's done. If it's PySCF stuff, if you are running any DFT calculations, there are more videos in detail about theory of DFT and all that kind of thing. And people always upload Gaussian videos on YouTube, so you can look at those. But the reason that I'm creating these workshops is because I felt that there was a need for bridging the gap as to how to run these quantum chemistry calculations in Python and code them, because it usually ends up clicking some buttons and you just run it, but it won't give you all these in-depth things of how to run it with code. So this is the reason I created this entire series where we just use Python and try to code stuff. And all the videos on YouTube channel are based on that. So that's the reason I'm creating those videos. It'll be pretty much unique because all of them will be from my research experience and trying to bridge together different materials. It's not just one thing that we have in here, but it's a variety of things and how it's applied for chemistry. And that's where a little bit of stress is on. So, but you may find individual topics when you Google search something as to what is a TDDFT. You may find resources on YouTube too about TDDFT, more in-depth ones. So, and all these materials are on YouTube, so you can just check the YouTube channel for the videos, and the link to these Python file, the Colab notebooks, it should be in the description. So there's another question: compared to other codes, can PySCF used for production? PySCF is used for production. Some of the articles you'd see PySCF is used, and if you're again using any of these for your own research, I would not do it in Google Colab, but run it locally. And if you want to see how to set this something like some of these codes locally, I would suggest look back at one of the videos on setting up environment for Python in chemistry, something like that on my YouTube channel, and that tells you how to set it up. And that's what you would need to do to set up these things on your local machine or on HPC, a high performance computing cluster, and you should be able to run these calculations. And yes, people do use PySCF for running it. Comparison of how fast this is with other codes, there may be some studies, but the reason I used it in this is because it's easy for me to do it on Colab. So that's the reason I used PySCF. But the things that we again discuss here should be applicable to other things that we should be applicable to other quantum chemistry codes that you use. But there may be some ways in which it differs, like how we are going to actually code it may differ, but it should still be the same. So there's another question: is PySCF for GPU? I recently looked up, and there was one of that in the survey, but yeah, PySCF for GPU, they do have PySCF for GPU, and if you search for GPU for PySCF, so this is the plugin that I found yesterday when I was looking through the questions, and you can just include one line of code and it should do on GPU. So I think device should be GPU and then on GPU. So it should work on GPU. Okay, so thank you everyone for attending this workshop. And if you have any comments or questions, do let me know on Facebook. And I hope the workshop met your expectations. If not, do let me know in the survey, the link of which is over here. And I hope to see you sometime soon when I conduct other workshops.
The recording has stopped.
Thank you all. And I've stopped the recording, so if you want to unmute yourself or turn on the video or something, it's fine, or you won't be captured anymore. And okay, so again, thank you everyone. So stay safe. Until next time.